Hello everyone. Today we're going to go a little deeper into black holes and their properties. Before watching this video, I recommend that you watch my previous video introducing black holes. Here we're going to look at charged black holes, rotating black holes, and how they're different from neutral non-rotating black holes. Before I get started, I'm going to assume you've learned the math behind the Schwarzschild metric. This video is going to be a little more technical than my other videos, so just a note of caution. Let's begin with the charged black hole. A charged black hole occurs when there's a net electric force in the space surrounding our black hole. We can describe this physically by adding an electrostatic term to our line element in the Schwarzschild metric. Recall that in our Schwarzschild metric, we obtain an event horizon when the term approaches 0. We can apply the same strategy here, except that instead of one event horizon, we find that there are two. We get this by reparametrizing our variables. This is the main key difference between charged black holes and a neutral black hole. Without going into too much detail, what this means essentially is that it's possible for you to reach a space-like trajectory inside the event horizon. Now this should seem surprising to most of you. Why? Well, for neutral black holes, once you cross the event horizon, you are forced into the singularity. This is not true for a charged black hole. You're free to roam around. You can't escape the event horizon, but you're still free to roam around. Quite interesting, right? Now, let's look at the case of a rotating black hole. Similar to deriving the equations for a Schwarzschild metric, we would need to work through the derivation for a Kerr black hole or a rotating black hole. We do this by applying the conservation of angular momentum. We'll find that the coordinate angular velocity is actually not 0 as we get closer to the event horizon. That's insane. What that means is that when we fly straight into a Kerr black hole, we start spinning around it. We will gain angular momentum just by falling in. That's incredible. Scientists call this effect the dragging of inertial frames. This is a special effect that makes Kerr black holes different from non-rotating ones. Another effect that makes Kerr black holes different from non-rotating black holes is the Ergo region. This is a region where motion must occur. It is a region where it is quite literally impossible to stay still. Where is this region, you might ask? Well, it's between the event horizon and a limit we like to call the stationary surface limit. This is another crazy effect, because suppose we are going close to the speed of light in the opposite direction, the Ergo region will slow us down and force us to be rotating with the black hole. There's no escaping it. Unfortunately, as cool as Kerr black holes sound, they have yet to be observed. The same goes for charged black holes. They seem to just evaporate too fast for us to measure them. Charged black holes and rotating black holes are very interesting fields of study in theoretical physics, and there's a lot of work going on about them. Understanding them has tested some of the smartest minds of our generation, and if we can understand them better, we will unlock more secrets of the great unknowns of the universe.